I'm currently working on this Televideo TS800A, and it's a combination dumb terminal and Z80 computer. So it contains a Z80 processor and a 6502 processor. The 6502 runs the dumb terminal and the Z80 runs the computer. And during this process I've shown some work in the firmware, disassembling the firmware and using the logic analyzer to trace through it. And that's something I've shown in quite a few previous videos. But I've been asked to show how I go from the image that's in the ROM to going through the disassembly process and how I get the disassembled code into a readable format. And that's what I'm going to look at in this video. I'm not going to go into a huge amount of depth in this, just the general process. And it does vary a great deal depending on the nature of the machine, the type of processor that the machine contains, the nature of the code and that sort of thing. And it also depends a great deal on the amount of technical information that I have available when I'm working on the machine. Luckily with this machine I've got quite a lot of technical information. I've got the schematics, and that really helps with this type of work because it saves a lot of trying to figure out what's going on within the machine. So the first step in this process is to extract the data from the ROM. So in this case we'll be looking at the firmware in this ROM. So this is the firmware the Z80 uses, and it's fairly straightforward in this machine. It's quite a small ROM, it's only a 4K ROM, so there's not that much source code in it. So it will be a good candidate to show this process, so it won't be too cumbersome, it won't be a huge file we end up with. But it will be a bit of flitting back and forth between the schematics, the board and the code, just because it's not a linear process. You need to look at the ports that are in use, the way they interact with the hardware and the way that's handled within the code. Normally it's kind of a seamless thing. Once you've done it a few times you kind of go through it automatically, but trying to video it, I've been trying to figure out how I can make this make as much sense as possible for anyone that hasn't done this. If it's the sort of thing you've done a great deal of, then it should all be second nature, but if it's not something you've done or seen before, it might get a bit confusing, but I'll try and keep it as straightforward as possible. So the first step is we read the ROM in the ROM reader. I'm not going to show that, it's fairly straightforward. Just basically plug the ROM into the reader and tell it to read, and what we end up with is a binary file. But we now need to turn that binary file into a human readable format that we can start working with. So we'll go over to the PC and we'll disassemble the binary file and start working to make it readable. So at the PC I've got a couple of the technical files that are for this machine. We'll come back to these in a little while. Quite useful and just save us a lot of time. But the first thing I want to do is start up the software I'm going to use to disassemble the code. There are quite a few available, but this is one I quite like. It makes quite a nice job of disassembling. This is the same software that I use for developing the code for the Z80 project, and it's got a nice disassembler built into it. So if we go to Tools, Disassembler, we then open up the file we want to disassemble. That's the binary file that was read from the ROM. So we open the binary file. It doesn't really show in here, but what we then do is we click on Disassemble, and what we end up with is this listing of the source code. So what we can now do is save that. So I'm going to save it as the name of the IC just to make it easier to reference later on. So we save that. We can now close this software, and we can use something like Word to open that file. So if we open up Word, we can use that to open the file. So we'll open this file and we end up with the listing that we just saw. So this is the file that we've just created using the disassembler. Now if we start reading through this, you can see that everything is just in continuous text. It's not particularly easy to read through, What I like to do to start with is to break this down into the individual sub-assemblies. Now on a file this small you could probably just manually go through it, do a find, and then each time you find a return you could just follow it with a new line. But what I tend to do is, this is why I start with Word, we'll change to WordPad in a few minutes, but I start by just doing a find and replace. So what I want to do is find all the returns and then replace those with a couple of, or follow those with a couple of blank lines. We don't want to do that with all the returns, but we will manually go through and correct a few in a few minutes. But the first thing to do is to get some separation between what are most likely the end of functions and the start of the next functions. So if we do a find and replace, so the issue here is we don't want to just blindly replace everything, because if we just blindly replace the returns, then anything with an RET in it will also result in several lines following on from it. So for example, if there are any return from interrupt functions, they will be split up into a return, RET, a couple of new lines, and then an I, which we don't want to do. So what we're going to enter in here is a space. That's what will precede the instruction, RET, and then we want to include the new line character. So we press Shift and the 6th character, and then P, and that will then search for a space, the RET, and a new line, and then we want to replace that with the start of the next line, which will be the same, so RET, and then we want some additional lines, so space 6p, so we'll do 3 of those. It gives us a nice spacing, and what we can then do is just do a replace all. So you can see it's made 59 replacements. So if we go through, you can see it's separated everything into fairly nice, what could be functions. We'll come back to these in a few minutes, some will need correcting, and we'll do this one more time. But this time we want to look for return from interrupts and replace those. So we'll replace all. It's only found one. Now if we didn't include this new line character here, then it would have split this return instruction and put a couple of spaces between the return and the I, which we didn't want. So doing it this way, it makes sure we don't split up anything that we don't intend to. The next thing we have to do is go through and just very quickly find all the returns, and now easy to spot of course. And what we're looking for is if a return instruction was preceded by a selective jump, a conditional jump that would jump over the return instruction, then we don't want to have a new line after it. So for example in this case we don't want these new lines because this is not the end of the function. Normally it is, so this is the quicker way around of doing it. In this case I will get rid of the lines, and the same with this one. Again we've got a conditional jump that would jump over this instruction, so it's not the end of the function. And one more down here, and we just keep going. Now sometimes if it's jumping back, then it could still be the return of the, or the end of the function. So we need to be aware of that. That's an example there. And I'll just go through and finish the rest of these off. Okay, so I finished all those, and it took about 30 seconds or so. Very quick process on a file this small. You can do additional searches and replaces if you want to save a bit of time. The next thing we want to look at is make sure we've properly identified the interrupt. So we'll do a search for that. And it has, as you can see, identified the interrupt. Doesn't know what the start of it is, so we need to identify the start of certain bits of code ourselves, and we can see here that this is the end of the previous function, so we can split this, and we can now start commenting on this. So we can, for example, just identify this as the interrupt handler. The next thing I want to do is to try and find anything such as an interrupt vector table. So we want to find out what mode the interrupts are going to be in, and you do this differently with different processor types. So we're going to do a search, and in the Z80 case we're looking for the instruction IM. Now it's going to of course find anything else. So we put a space before it, it'll give us a better chance of finding this more easily. So we'll do a find next, and straight away we found what we're looking for. So it's interrupt mode 2 that we're looking for, so there will indeed be a vector table. So to find the vector table, we now need to find out where it's loading the interrupt register within the Z80. So we'll do a search for that. Okay, and we've found it second time. So this instruction here is loading the internal Z8 register as a pointer to the base of the address that's going to be jumped to when a mode 2 interrupt occurs. So in this case the value it's loading is shown here, and so it's 40 hex. So if we search for the address 40 hex, it's most likely going to be the vector table. And again, this varies depending on processor type. The 6502, for example, you'd have to do this differently, but it's the same type of steps in the process. If we now go back and look at that address, so remember we're looking for address 40, and it looks fairly promising. So we've got a couple of knobs here for no apparent reason, and they're right after a jump. So in other words, this code can't be ever got to, because if you come here you just jump straight to here, so most likely that is the end of the vector table. So what we have here is what I believe would be two vectors. We'd have that one, and the next one is going to be 0370. And if we go to 0370, we end up here, and you can see this confirms what our suspicions were, and we found the interrupt handler and we found the vector table. So we've already identified some of the code here very quickly. It's taken 5 minutes so far to do this, and that's with most of the time me talking and trying to explain it. So this is a very quick process, and of course each time you find a bit of code and identify it, it becomes easier because there's less code that's not been identified. Now the next thing is to look at how the code interacts with the hardware. So in this case what I would do, because this code is controlling hardware, is I'd search for any out instructions. So we're going to search for out. So we found one here, and the port, so the number in brackets is the port number. In this case it's 20 hex. If we look at the next one, then you can see that this is 10. What I'm going to do now, because I prefer using WordPad for the next part of this, I'm going to copy all this into WordPad. I just prefer the way that WordPad allows us to search through the text. So I'm just going to quickly copy this into WordPad, and then we'll continue. Okay, so we have it now in WordPad. We'll get rid of the Word version, don't need to use that anymore. And we can now start search. This tends to be a lot easier and simpler to use. We don't need all the bells and whistles that are in Word. So again, we can start searching through the text. So we found the first one again, second one. And what I want to do is identify what these out instructions are likely to be controlling, because that will tend to give us a good clue as to what that particular function is doing. So there's a couple of ways we can do this. The easiest way is to look at the way that the the ports are decoded. So if we open the technical document we have here, and I'll scroll down to the relevant page. So I've selected the part of the schematic we're interested in. This is the out port decoder, and it's just a simple 3 to 8 line decoder chip, 74LS138. So one of the 8 output lines will go low, and which line goes low depends on the binary value we put on the 3 inputs that are labelled A, B and C here. Notice they're being driven from address lines 2, 3 and 4, not 0, 1 and 2. And I'll come back to why it's like that in a few minutes. But if you're familiar with the way that the Z80 accesses and controls its in-out ports, when you issue an in or an out port instruction, the Z80 will put the required port address onto the lower 8 bits of the address bus. Now in this case, because we are selecting the output of this device using address lines 2, 3 and 4, it means that address lines 0 and 1 can be used to further select registers or devices within a given port. So for example, if we look at the outputs of this, you can see it's fairly obvious what each one is controlling. If we look at the third one down, it says CTC chip enable. Now if you recall, the port numbers for the CTC chip were 8, 9, A and B. So if we go back and look at the inputs, if we select port 8 for example, then that will result in address line 0 being low, address line 1 being low, address line 2 being low, but address line 3 will be high. In other words, what we'll have on these inputs is 0, 1, 0. And that means that the Y2 line will go low. In this case that's the CTC chip enable. But if we select port 9, that means that address line 0 is also high. So we're still selecting the CTC because we're looking here at address lines 2, 3 and 4. So the CTC chip enable line still goes low, but also the address 0 line can be used to select the second register within the CTC chip. So it gives us a nice way of breaking the ports into groups of 4, and so we can select any one of those 4 subports within each group depending on the port that we select. So now we know how this works, we can figure out what each port is actually doing. So if we open up the second of these technical documents, and I'll scroll down to the page we're interested in. Okay, so looking at this page, this tells us what port controls which device. So in this case, port 8 is indeed CTC channel 0, port 9 CTC channel 1, and as you can see we can select the 4 registers we're interested in through the single port output that enables the CTC chip enable. And in this manner we can go through all the port accesses in the listing and identify what each one is trying to control. Now some are missing, so for example in the listing it uses port 18 and that's not shown anywhere here. But if we go back to the schematic, then we can work out that port 18 is actually controlling the floppy disk drive select line. So using the schematic and this listing and the technical document, we can actually figure out what all the port accesses are. So if we now go back to the listing, we can search through all the port accesses, whether it's an input port or an output port, and we can identify what each one is. So for example, port 0 is the dip switch, and we know that because this is an in, we are going to read the dip switch. Okay, and it's as simple as that. You just go through figuring out what each out or in instruction is trying to control or read. You can comment it, and by the time you've done that you can normally figure out what each one of these function blocks is actually doing, and that's what you saw me using in the previous video when we were going through and there appeared to be comments already there. All I've done is go through the code beforehand, figure out what each port was controlling, have a rough guess as to what I thought each block of code was doing, and commented it accordingly. Now this process gets easier the more times you do it, so once you've done this 30 or 40 times, you can just kind of see fairly quickly exactly what the code is attempting to do. And the other thing that's worth looking at is if you see code that just doesn't make sense. So if you're seeing the same register being loaded over and over again, for example, I'll try and find an example of it if I can. So for example here we've got the L register being loaded from the A register twice in a row. That's not something you'd normally do in code. You might have a specific reason for doing it, but most likely it means that this is data rather than code. And so as you go through and start dividing it, look for any calls where one of these addresses is being loaded into a pointer register, and then more than likely it's the start of a lookup table rather than an executable block of code. Now by the time you've been through this, it usually takes on a file this size 2 or 3 hours to go through and comment it as far as I can. By the time I've done that, then the code starts to become quite readable, and then once you start using the logic analyzer to go through the code as it executes, you can clarify this and add to it, and it all becomes much clearer. So it's quite an interesting process to go through. You can learn a lot about different coding techniques, different ways that the people that develop these systems, very smart people, they develop these systems, and there's some very interesting code constructs, and it's also interesting to learn how the machine works, and of course it's extremely useful when you're trying to repair it. So we'll just have a quick look at the code that I've commented and the one I've been using for the repair. Bear in mind here that my objective is to repair the machine, not to have a fully commented code file. But you could take this as far as you wanted to, and if your goal is just to disassemble the code and fully document it, then you could spend far more time going through this. But you can see that I spent probably 3 hours on this, going through and breaking it into functions and trying to get it properly commented, so that I can use it for the repair. But you can see that even after a fairly short time that the comments are starting to identify what each block of code is doing. So as you go through, and especially as you focus on bits of the code that you're interested in because it's part of a test, for example, that's failing, then you can add more detail to the code. You can figure out exactly what it's trying to do at any part of the code, and it all becomes much more readable. So it's a fairly straightforward process. It can be time consuming on more complex firmware jobs. Sometimes you'll have far bigger files to deal with, and it's the same process, just takes longer. But as you can see, the comments do make this entire thing far more readable, so you can go through it, and especially when you're using the logic analyzer, you can figure out far more quickly what's going on. And as you go through the repair, you can add more comments, and it all begins to make life a lot easier. And it's certainly a very useful tool for carrying out repairs. If this is the sort of thing you want to see more of, then leave a comment. I realise it can be quite boring just staring at the screen and listening to me talk, but if it's something you're interested in, then let me know.